Hi guys, and welcome to a video about data visualization in Python using Matplotlib. So the first thing that we're going to do is we're going to load up a Jupyter notebook. So the way that we do that is we have to navigate to the terminal, which is this thing here. If you're using Windows, then you're going to want to hit the Windows key on your keyboard and type CMD. That should bring up the command line option. So if you click that, it should load up something that looks slightly similar to this. It's basically a black box where you can type things in. That is how we're going to access the Jupyter notebook. So what we need to do is type Jupyter notebook. And if all is well, that should load up in our browser automatically. And then from there, we can navigate to wherever we've saved our notebooks. So for us in this lesson, it's going to be an introduction to Python and in Matplotlib. So we'll open that one up. So Matplotlib, what is it? Matplotlib is a Python library. Now, a Python library is basically, you can think of it as sort of external pieces of code that someone else has written, which you can import into your own projects, and it makes life a lot easier a lot of the time. There are lots of different libraries out there, and Matplotlib is one of the most popular ones for making data visualizations. So you can see that here we've got some examples of the types of thing you can make with Matplotlib. We've got here a kind of line graph. Here we've got some kind of scatter graph with lots of different bubbles of different shapes and sizes. We've got some more here, more complicated ones, and some 3D ones down here. So there's basically loads of different things that you can make with Matplotlib, and you can check out this link here where we've got a kind of more complete list of examples of things that you can make with Matplotlib. So as you can see, there's tons of different things you can do with it. If you see one that you think is interesting, you can just click on that and that'll take you to directly where the code is written to make that plot. So if you see one you like, then you can always go in here, copy and paste this code into your Jupyter notebook and try and run it and maybe try and edit it to see how it's done. Okay, so the first thing that you need to do is install Matplotlib. So assuming that you haven't done that already, then you would need to open up another terminal. So I've got another one here. On Windows again, you just have to type command line and get a new one up. And then what you're going to do is type pip, P-I-P, install Matplotlib. If I hit enter on that, so for me, I've actually already got it installed. So you can see here it says requirement already satisfied. I don't need to actually do that. But for you, you would get some kind of, it would go away and it would download it and it would install it automatically. So the first thing we do when we use an external package is we have to import it. Okay, and the way that we import it is by using this statement here. We go import and then the package name. And here, if you see, so we've got matplotlib.pyplot. Now, pyplot is a kind of sub package within Matplotlib that is really useful. So that's what we're doing here. We're importing matplotlib.pyplot. So that's a specific thing within Matplotlib. And then this here saying as PLT, this means that basically we're going to be able to access all of the Matplotlib functions through this variable we've just created called PLT. So you'll see what that means in a minute. Basically, if we didn't do that, if we just said import matplotlib.pyplot, that would also be fine. But then every time we wanted to use a specific function within Matplotlib, we'd have to type out matplotlib.pyplot. Whatever the function that we want to use. So that as PLT just is a shorthand and it just allows us to write things out a bit more quickly. So if we hit enter on that, so there we go. You see a little star and you now see that that's run. That means that we now have imported Matplotlib and we should be able to access all of the variables through this PLT thing here. So if you haven't done the install, you're going to get some error at this point. But if you get no error, if nothing comes out, then that's fine. Matplotlib has been installed and you're ready to go. Cool. So the other thing that is quite useful when you're using Matplotlib in a Jupyter notebook specifically is this little thing here which says %matplotlib notebook. Now that basically allows you to get kind of nicer, more interactive plots. And for some reason that I've really never worked out, you have to run it twice. So we're going to run this cell here, got another 2 there, and we're going to run it again. So that's been run twice. So now that is going to allow us to have those interactive plots. Okay, so the first kind of plot we're going to look at is called a scatter plot. So this is a really useful type of plot that you will see again and again in all sorts of data science applications. And it's kind of when we want to look at the relationship between two variables. So you could say, for example, a population of people and you're looking at height versus weight. Say you might expect that the taller someone is, the more they weigh in general. But obviously that's not going to be a strict relationship. There's going to be some variance there. But a scatter plot can allow us to have a sense of the overall relationship between two things. So that's a bit abstract. Let's go and look at a specific example here. So we're looking at an ice cream business. So we run an ice cream business and we want to understand how the temperature on a given day affects the number of ice creams we're likely to sell. So we go out and measure the temperature on every day over July and August, and then we add up all the revenue from our ice cream vans that we make on that particular day. So this gives us a set of pairs. For each day we've measured the temperature, and for each day we've measured the amount of money that we've got. So we can visualize that relationship by scattering all of those points on a graph. Okay, so say we've got roughly 60 measurements of temperature and revenue, and then we're going to have 60 points on the graph, and the kind of horizontal distance is going to represent the temperature and the vertical height will represent the revenue. So how are we going to do that? We're going to look at some data here. So this is the temperature reading. So if you remember from the previous notebooks, what we've got here is a list. So we're saying the temperature equals, and then we have this list of values all separated by a comma. They can run onto separate lines, that's no problem. But what we've got here is just the temperature reading on each day. So the first day was 20.2 degrees, the second was 22 degrees, then 18.6 degrees, etc., etc. And that has all been stored in a list separated by commas. Okay, so we've got these square brackets indicating it's a list, and we've got all of our observations here. Now we've got an equivalent list, but this time it's for the revenue. So we're creating a variable called revenue, and we're assigning it this list here. So this is another list. So this day we made £435.83, £466.11, etc., etc., etc. And basically each one of these is paired across these lists. So for example, on this day it was 20.2 degrees, and on that very same day we made £435.83. That day was 22 degrees, here we made £466.11, etc. So these are kind of paired across these two variables. So the way that we can plot that relationship is using this function called scatter. But the very first thing that we always want to do before we make a new figure is this thing here, this line here, which says plt.figure. Now that just tells Matplotlib that we're starting a new figure, and whatever follows we want to be plot to that figure. So we're going to go plt.figure, and then we're going to write plt.scatter. So this is a function. So we're going plt, which is our pyplot, our Matplotlib thing, dot scatter, and then we're going to open brackets, and we're going to put in two things, right? This is going to be our x coordinates, and this is going to be our y coordinates. So in this case, our x coordinates is the temperature, and our y coordinates is the revenue. So when we run this cell, we will get, temperature is not defined, so we have to run these cells first. So we're going to run that one, and we're going to run that one, and then we're going to run this one. Great. Okay, so this is our data. So you can see along here, we've got the temperature, which ranges from about 18 degrees to 32 degrees. And here is our revenue, which ranges from about £350 to £650. And you can see that there is some kind of relationship going on there, but it's a bit random, but it kind of seems like roughly the higher the temperature, the more revenue we make for our ice cream business. Cool. So looking back at this plt.scatter, so we've got plt, the keyword for Matplotlib, scatter is the function. So we're going plt.scatter, and then we're passing in two arguments to this function. The first being our x coordinates, and the second being our y coordinates. Now these two lists have to be the same length. If they're not the same length, you're going to have a problem, because it assumes that they're paired up, right? So x1, y1, x2, y2, etc., etc. But that all being fine, you should get a nice plot out the other side. But this plot's a bit incomplete because usually when you see a graph, you'd like to see some labels. I mean, without labels, we have no idea what we're looking at. So the way that we can do that is using some more Matplotlib functions. So again, we start with plt.figure, we scatter the temperature and the revenue, and this time we'd use another command, which is plt.xlabel temperature. So what that means is that it's going to put a label on our x-axis called temperature. Now, we could call this whatever we wanted. We could call it random x label. That's also fine. But the thing to remember is that it has to be in these quotes because it's a string, right? In Python, it's a piece of text basically, and all text has to be kind of captured in these strings. If it's not a function, if it's not a variable, if it's just a piece of text, then it's most likely going to be found in between two quote marks. So we could do the same thing for the y label. So we've got plt.ylabel revenue and plt.title. That sets a title up at the top here, which you can see. So we'll run that. Cool, we've got a title, we've got a y label, and we've got now this has been changed to random x label. Let's put that back to temperature. Cool. So the first exercise is about units. So all that you have to do for this first exercise is go back to this piece of code here and change those strings of temperature and revenue so that they have the units in. So what is the temperature being measured in? What is the revenue being measured in? It's always useful to have units on your graph so that it's clear. It's not Fahrenheit, it's not dollars. It's a specific unit of temperature and it's a specific unit of money. So that should be clear on your plot as well. Okay, so colors. That's a pretty boring plot. It's just this one shade of blue. There's lots of colors out there that we could use, and the way that we do that is in the scatter function. So if we want these points to have a specific color, then we can go plt.scatter temperature revenue and then color equals something. Okay, so in general there are lots of different extra arguments that you might be able to pass into scatter. You can tell them what size the points should be, you can tell them what color they should be, you can tell them what transparency they should be, etc. So you have to be clear about which one you're talking about. The first two are always clear because the first one's always X, the second one's always Y. But beyond that, you need to specify what it is that you're trying to affect. So in this case, we're trying to affect the color. So we say color equals, and then we have to pass in a string which tells Matplotlib what color to use. Now, of course, some color isn't a color. That's just an example. You need to give it a specific color, and I'll show you in a minute the different colors you can use. But one thing to notice is that this is color spelled C-O-L-O-R. The American spelling, a bit annoying, but we've got to deal with that as Brits. So yeah. So these are the selection of colors that you can choose from. As you can see, there's lots of different ones here. Any of these will be fine. You just pass in, so for example, if I wanted this lawn green, I would just, instead of some color here, I'd put in quotes lawn green, and then it would come out this color. So for exercise 2, you just have to copy and paste that code and choose a different color. Great, so multiple scatters on one graph. It's often the case that we don't want to just see the relationship between two variables for kind of one set of data. We often want to compare the relationship across two different things. And in this example, I'm looking at the weight and height of table tennis players versus weightlifters from the Olympics. Now, this is actually real data. I took it from here. You can have a look at this. This is a website called Kaggle that hosts lots of different data sets. So this is called 120 Years of Olympic History, Athletes and Results. So we can come down to the data source here, and you can see they've got the names of these athletes, their gender, the year that they competed in, and one of the things they have is their height and weight. So I really did take this from, this is real data about real table tennis players and weightlifters. So you can see along here they have the sport that they're doing. Yes. So you can see here we've got TT height. So this is the height of the Olympic table tennis players in centimeters. So this is just a list. So this guy was 170 centimeters. This guy was 176 centimeters, etc., etc. And along with that, we've got a list of the same length, which is representing their weight. So the same guy, this guy was 72 kilograms. This person was 107. This person was 74 kilograms, etc., etc. And I've done the exact same thing, but for the heavyweight weightlifters. So you might expect that there's a bit of difference in the weight between weightlifters and table tennis players, but we will be able to see that. So if we run this cell, we can go down here. And now one of the important things about graphs where you have more than one thing is that you're often going to want to put a label in. So we've got the same thing here. We've got plt.figure, and on this line we're going to scatter the weight of the table tennis players versus the height of the table tennis players. And we want to give this a label. So we're going to say, in this case I've just got it as my first label, but that's not a very good label. So let's put this as table tennis players. And here, this is the weightlifters. So we'll put weightlifters. And remember, this again has to be in quotes because it's a string. And if we do that along with this command here, which is plt.legend, this basically says, okay, put a little key up in the corner which tells us, which kind of labels the two different parts of the data set. And again, we've got an X label, a Y label, and a title. So let's run this. Okay, cool. We now have a scatter plot which has the weight along one axis, the height along the other axis, and we can see the difference between table tennis players and weightlifters. So you can see the weightlifters generally having a higher weight. Not always true. There are a couple of absolute beast table tennis players up here as well. But in general, you can kind of see a pattern where weightlifters tend to have a higher weight and table tennis players tend to have a lower weight. Interestingly, there's not too much of a correlation in the weight between the weightlifters, between the weight and the height of the weightlifters. It's kind of a bit random. You've got some, really heavy but not phenomenally tall weightlifters over here. And this guy, over here is super light for a weightlifter, but not super short. Whereas the table tennis players, there seems to be a bit more of a relationship. So as I said, there's this absolute monster who's almost 2 meters over here. Don't know who he or she was. And he's pretty heavy. And we've got this teeny tiny little table tennis player over here who was both very, very short and very light. Maybe there's some kind of interesting bit of information to be taken from that. Who knows? Okay, so just breaking down that line again, we've got plt.scatter. We've got the x variable, the y variable, and we're also passing into this function a label. So again, this was kind of like color. So up here we had color equals some color. Down here we're passing a label. And again, it has to be in quote marks. Now, this on its own won't bring up your little key over here. You have to tie it with this line which says plt.legend. That's important. Otherwise, it just won't appear. Cool. So for exercise 3, try changing the labels and see what happens. And you can also go in and add some colors to each scatter plot. Cool. So now we're looking at line plots. So line plots are a bit different to scatter plots in that they are a line rather than a scatter of points. And they are more useful for when you're kind of talking about a thing that's maybe changing over time, or maybe there's some strict relationship between two things. So maybe you want to plot a graph of x squared, or a kind of time series of a stock price or something like that. Something that's not a random relation between two things. You have something that's quite that's sort of changing. It has a specific order and it's sort of changing over time or something like that. So in this case, we are looking at a situation where there's a biologist who's studying the multiplication of cells under a microscope. So she's looking at some E. coli bacteria, and every half hour she gets a computer to take a photo of this group of cells, and the computer counts the cells and puts that into a list. So over here, we've got a list saying the time at which the measurements were made. So this one was made at time 0, this one was made at the first half hour, this was made at the first hour, etc., all the way up to 24 hours every half hour. And then over here, we have the count. So this is the number of cells that were counted by the computer at that time. So you can see it's growing. So this is the kind of situation where we might want to have a line plot. So I'm going to run that cell. So let's just run this one here. So what we've got here is, again, plt.figure. We always have to start a new figure with that to make sure it's going onto a new one and not being replotted back onto an old one. So we're going plt.figure, again, open and close brackets. And we're doing plt.plot our count. So this one is actually pretty similar to scatter in a way. So in this case, we're plotting the time along the x-axis and we're plotting the number of counts along the y-axis. So again, we're going to have the first variable being passed into this function is going to be the x variable, and this is going to be the y variable. And if you look at this plot here, we've got a case where it's growing pretty rapidly, and then it sort of ends up growing at quite a constant rate, and then the growth sort of slows down and we peak out at some sort of maximum value of the number of E. coli bacteria. Cool. So to reiterate, this is the function plt.plot, and it takes in an x variable and it takes in a y variable. These have both got to be some kind of list which are of the same length, which are kind of paired measurements, paired x, y measurements. So in this case, our x is the time and our y is the count. So yeah, this one's just saying that, yeah, it's pretty similar to a scatter plot, except you could think of a line plot actually as being the same as a scatter plot, except rather than just points being drawn on the screen, you have lines connecting those points. Cool. And again, we can do the same thing with labels and titles and colors and that sort of thing. So this exercise here, exercise 4, says just try changing the color and adding axis labels to above plots. So this is going to be very similar to the stuff we had up here. We're just going to add some colors into this function. So instead of plt.plot our count, it's going to be plt.plot our count, and then some optional extra arguments that we have to pass in. So you can basically copy and paste the code from above and just change a few things to make it a line plot of this. Okay, so as we could do multiple scatters on one figure, we can also plot multiple lines. So the idea here is that the biologist has come up with a new gene editing technique that's designed to slow down the rate at which this bacteria can multiply. So she's first done it with the unedited bacteria, the unedited E. coli, and then she's gone in and edited the genes of this E. coli bacteria, and she's repeated the experiment. And she wants to see if the growth rate is significantly different between the two types of bacteria. So again, she measures the number of cells that are present every half hour for 24 hours, and this time she gets this count data. So again, you can see it's growing. It's difficult to tell from just this alone what the relationship, well, how it grows compared to the normal bacteria. So if we hit enter on that, and now we're going to just run this cell here. Cool, so now we can see a comparison. This blue line is the same as before, it's just the hour and the count, whereas this one is the hour against the count edited, which was this variable here. So this is the count for the bacteria with the edited genes. Okay, so exercise 5 is basically just to sort this graph out. So this graph alone is not very informative. We don't know what we're looking at. We don't know what the difference between these two things are. This alone basically gives us no information. So your task for exercise 4 is to go in, put some axis labels, give it a title, give it a key, add some bright colors, and basically make this graph a lot more understandable and pretty looking. Cool, so the final plot that we're going to look at is called a histogram. Now, you may or may not have come across histograms before in your math classes. So to explain what a histogram is, we're going to take a little detour into space. So this here is a picture taken from the Hubble telescope. which is mounted on a satellite that orbits Earth, and it can take these really sort of high resolution photographs of very, very distant stellar objects. So basically, if you look at this, each one of these things is actually a galaxy that is going to be billions of light years away. Now, a light year is an extraordinarily long distance. It's the distance that light travels in a year. So light you can think of as being unbelievably fast. So how far does an unbelievably fast thing travel in a year? Unbelievably long is the answer. So this is a real picture taken from the Hubble telescope, and every single one of these is a galaxy which is many millions or billions of light years away. So astronomers, when they take these things, take photos of these types of things, they need to resort to statistics because they're dealing with such a huge number of objects out there. The only real way that you can deal with them is with statistics. So a little bit of physics here, just as a kind of small detour. When we look at these galaxies that are far away, one thing we might want to know is how far away are these things, and kind of what is the distribution of distances. So we might expect that some galaxies are closer to us, we might expect that some galaxies are really far away, but how does that work? Are there loads close to us and not so many far away? Are there loads far away and not so many close to us? That's a legitimate question that we might want to answer. So the way that physicists do this is they look at these pictures of these distant galaxies and they measure something called the redshift. So you might have heard from your physics classes that the universe is expanding. And if the whole universe is expanding, that means that things that are further away from us are traveling away from us faster. Because you could think of it like, imagine if you sort of draw dots on a balloon and then inflated the balloon. Dots close to each other will be moving away from each other kind of slowly, but dots that are kind of a little distance apart will be moving away from each other faster. So that's the general idea. So we've got this expanding universe and we've got more distant galaxies moving away from us faster than more close galaxies. Now we can measure the speed at which galaxies are receding from us by measuring the redshift. So the redshift is something like that situation where you're on the street and an ambulance goes past, and as it's coming towards you it sounds kind of high pitched, and then as it's going away from you it sounds kind of low pitched, and that's because the waves are basically getting bunched up when it's coming towards you and getting stretched out when it's going away from you. And the exact same thing happens with light. So if you have an object that's emitting light that's moving away from you, it'll appear more red as the light waves get stretched out. And as a light emitting object is moving towards you, you'll get the waves squished up and they'll appear more blue. So knowing that, we know that the stars that are, or the galaxies rather, that are more distant are going to appear more red because they're moving away from us faster, and the galaxies that are closer to us are going to appear less red because they're moving away from us at a slower rate. So if we look at a distant galaxy and we say basically how red is it, then we can estimate how far away it is. So this was all a big detour to explain this big old list of numbers we have here. So the physicists have basically gone out, they've measured how red these distant galaxies are, and then they've used that to approximate how far away they are in billions of light years. So for every single one of these galaxies, basically, they measure how red it is, and then they can kind of, from that, for every single one of them, estimate how far away the galaxy is. So this list here is a list of the galaxy distances in billions of light years. So this first galaxy was 31.61 billion light years away. You know, this one was 37.83 billion light years away, etc., etc. And we've compiled them all into a big long list. And if we hit enter on that, then we've just created a new variable called distances, which is this big long list of numbers. Okay, so the way that we create a histogram is very simple in Matplotlib. Again, every time we're going to have this plt.figure, which tells Matplotlib we're starting a new figure, and we're going to have plt.hist, which is a function for creating histograms. Now, if I didn't explain it before, a histogram is basically a way of saying how many values do we have between some range. So if we wanted to make a histogram of this data, first we might say, okay, well, how many galaxies are there between 0 and 10 light years? And then we would say, okay, how many are there between 10 and 20? How many are there between 20 and 30? How many are there between 30 and 40, 40 and 50, etc. And we can kind of make a sort of bar chart where the bar covers each interval, and then we just have on the y-axis how many galaxies were found within that interval of distances. So we can do that here. So we go plt.hist, and then this is again a function, and we're just passing in this list of distances, and that's going to create a histogram for us. So we get something like this. Along this axis here, we have the distance, and along this axis here we have the counts. So you can see, for example, here between about 2.4 or 2.5 billion light years away and about 6.4 or something, 6.8 billion light years away, there were roughly 5 galaxies that were counted in that picture that were between that distance. And over here, you know, we've got more. So you've got this kind of interesting feature where the further away you look, the more galaxies there are. So again, we can basically add all the usual things that we did before. So we can add an X label, a Y label, a title, and again we could pass in a color, for example. So in this example, I've aptly gone for the color called Deep Sky Blue. Again, we have the new figure as always. So we run this. We're going to get a slightly more intuitive plot now, which has the galaxy distance in billions of light years and the number of galaxies, and this kind of histogram here in this shade of blue. Great. But one of the things we might want to control for a histogram is the number of columns that we have, right? So instead of saying, you know, how many galaxies are there between 0 and 10, how many are there between 10 and 20, how many are there between 20 and 30, etc., etc., we might want to say, well, how many are there between 0 and 5, 5 and 10, 10 and 15, or, you know, how many are there between 0 and 2.5, 2.5 and 5, 5.5 and 7.5, etc., etc. So the way that we do that is by passing in a parameter to the histogram called bins. Now, bins is just basically another way of saying sort of how many ranges. So a bin is a range, you could think of it as. And if we've passed in 30 bins, then instead of how many have we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 is the default number of bins, but we can tell it to pass in more, which might be a good idea. If we've got lots and lots of data, then we can maybe work out a slightly more fine-grained relationship by passing in more bins. So that's all we're doing here. And you can see this time there's a greater kind of, well, the bins are thinner, or the rectangles are thinner, and we can kind of see a slightly more detailed relationship that we've got from our data. So for the final exercise, I just want you guys to try adjusting the bin number and see what happens. So if we have lots and lots and lots of bins, what's our histogram going to look like? If we have a tiny number of bins, what's our graph going to look like? And what do you guys think would be an appropriate number of bins for this data? So that's all. Once you've worked through all of that, you will have a pretty good idea of some of the most commonly used functions in Matplotlib.